Okay, we're going to do the coding for the Fick's law solution now. So you've already turned this homework up, had a look at everyone's homework. Now I'm going to go over my implementation of the solution and go over some things I've seen. Okay, so we already made the outline of this earlier in an earlier video. So let's just go over the completed thing here. So for my delta x and delta t's that were needed for this part of the solution here, a few things here. You want to keep your delta t small, definitely small compared to delta x. And we're going to do two diffusion constants, either a 12th or 0.5, depending on what situation we want them all. The 0.5 is the coin flip. The coin flip means you're always moving in steps of 1, so there it makes sense to do delta x as 1. If you do it smaller than 1, it'll still work. The normalization would be kind of weird. You'd still get basically the same general shape of your distribution, but there's no reason. It's losing data. But when we do the other one, the 1/12th, well, our delta x can be anything between 0 and 1, so you probably want to make this smaller. And we'll see in a minute what those solutions look at. But the thing is, keep delta t small compared to delta x. So that's why I'm going 0.01, because I'm not going to go smaller than that. And I've already coded it, so I'll just go over what I did. And I went over a lot of this already in the previous video. Just the engine of the solution in the for loops is all the new thing. So I have concentration arrays, C and C new, and they have a length. The length is determined by the time, because the random walkers, in theory, could just move ballistically the entire time. A few random walkers can do that. So I want plus and minus that distance, which is 2 times. So then I divide it by my delta x, which is 1, to get my length. And I'm casting that as an integer, a constant integer. So here I have definitions and constants. Integers, don't do variables in here. Just use constants and definitions. Global variables is kind of frowned upon. But that's an aside. So I do that. So, and then I initialize both of my arrays. I set them equal to 0. I find my halfway point. This is this h for halfway. It's 0.5 the length. It's an integer. And I say, okay, at that point, I'm going to put 100,000 walkers, because in my random walker simulation, I do 100,000 walkers for 100 time steps. And then I have this constant here, which is just diffusion constant delta t over delta x squared, which from here is just this guy right here. Simple as that. And then here's the main engine here. So this is where I update my C new, where my C new scans my C current, and then this is where my C new becomes my new C current, and then this is all just the time loop. And then when I get done, I just print this array from here. Here's where I saw some trouble here. So look at what I'm doing. I have 3 instances of the C new. One where C new, I'm looking at the 0th position, and one where I'm looking at the length -1 position, and one where I'm looking at the ith position. So why do I do the 0th position? Well, got to be careful. You don't want to step off arrays, right? So C new starts, or these arrays start from 0, and they go from length -1 because they have length spots in them. They divide the space into length variable spots equal length spots. So when I'm at 0, I can't look at the I -1. Remember, I, or the index here, is representative of where we're at spatially. So I don't have the -1 here, because that would be -1. That doesn't exist in the array. So that gets set to 0 right here. And then when I actually go into positions 1 through length -2, I can scan both adjacent ones, and this is just the default solution that we found, that I give you in the handout. And then at the end, the forward end, well, I don't have the +1 available to me anymore, because that's off the array. So that set that one to 0. So that's just set to 0 here. And I saw some people try to handle this in a weird way. and where they were actually saying like something like this: if I minus, in this case, yeah, del x or delta x is less than 0, which means the array is going to step off. Obviously, this would be, I mean, this is a bad thing I'm doing, so this is just an example of what I saw a lot, a couple times this, so just be careful. Then they just say, oh, if I equals 0, something like this. So the only time this is going to get hit is when I is 0. So if I is 0, I minus delta x, so, or the only time this is going to hit, so, okay, they did this, minus 1. So the only time we're going to hit I, this statement is when I is 0. So that means I'm looking after array. I'm saying C0 of -1, C, so I is 0, minus 1. So there's no spot there. You're putting this to 0, but it's a spot off the array. It might work. It might actually be okay in the long run, but it's dangerous because in some implementations, it's going to look at some memory address, which could be a very small or a very large number. And if it doesn't, in this environment here, it might be okay. It might see that and just zero it out. But if you run it in an application, this might just explode and you get a seg fault or something. Just be careful. Don't go off arrays. This is going on. This will go off an array. So we just get rid of that. Don't do it. That's just my aside here. Okay, but still, as it is right now, the solution is just fine. And if you run it, which I just ran this code for, let's say, with delta x of 1 and delta t 0.01 for a diffusion constant of half, well, you get this solution here. The blue is the solution. And you see there's all these little zeros. So there's going to be a lot of zeros. These are coin flips. We can go left and right. So there's a lot of things that are going to be 0. Like imagine you're at the first time step. 50% at the first time step, everything's at the 0. Then you take the first step, 50% go left, 50% go right. But none of them are in the center. Well, you integrate that over a bunch of times. You're going to have spots that are zeros. But you still have a nice normal distribution. Here is the actual histogram of my random walkers. This is the actual answer. And it's plotted in the background. It's the same thing here. You can't see it because they're essentially exactly the same. So it worked perfectly. I divided my space out into increments of 1, took a histogram from my random walker code, which we'll go over how to do that in a separate video, and we get exact agreement, which is great. Now, if I come back here and I go, okay, let's make this a 12th. And when I do this 0.1, 12.1, 12.0, 1.0, 12.0, I put the decimal there to make sure it knows that, hey, it's a floating point number. Make it double. And I ran this already, but it's the same thing. Now I can actually, here I'm going to actually make my delta x smaller because it can take steps smaller. So we do that. Run it, which I did through this, and then we can get our solution here, which is here. So now you see that 0 is at 1,000. I made my delta x 0.1, and there's 200, so that's 2,000. My x array is 2,000 spots, and each spot's 1/10 of a unit. So this array goes from 0 to 1 to 2,000. So there's 1, you go to the end, there's 2,000. And then all the actions happening in the middle. And I had 100,000 random walkers, so if you come here and look at it, you look at the sum, which is right here, it's 100,000. So that's another check, and make sure that the sum of all these guys, or the sum times tx, I guess, would be 100,000. And then, so this is the Fick's law solution. This orange line is the actual solution from 100,000 random walkers doing 100 time steps. Again, you sum, I had 100,000 random walkers, and you see perfect agreement. Well, it's a little chaotic here, but overall, you can hardly even see theoretical line. And that's it for the Fick's law solution. It should match the histogram of your random walkers perfectly, or near perfectly if you do it right. Things to watch out for: delta t needs to be very small compared to delta x. And make sure your delta x is something appropriate. Like if I'm doing coin flips, we're always moving steps of 1, having delta x 0.1 is not very smart. But on the other one where we're continuously having from 0 to 1, then yeah, you can go for a smaller delta x. It physically makes sense. And just be careful not to step over out of bounds on your arrays. The arrays go from 0 to their length minus 1, like whatever their length is. So make sure you never step out of it, because that could cause big problems. And that's it. And keep a look for other videos. I'll post a video on the how to do the histogram, and maybe some stuff on how to print more to files later. All right, bye.